So before we launch into that actual question, if we backtrack to, I think that's one we went through and solved. One of the conversations that we had was that if you're looking at a voltaic cell, you need a positive cell potential. So if you're looking at this kind of question, I need a positive cell potential, the quickest kind of cheat, if you will, would be to look at your reduction potentials over on the right-hand side and go through and say, well, which one's the most negative? Whichever one was the most negative, that equation you should go through and flip. Does that make sense? Okay, and that's great for cell potentials because what you're trying to target is getting the most positive cell potential possible, because that's the point of a battery, is generating positive cell potentials. What we've got to be careful of is that we aren't necessarily always going to have positive cell potentials. Right? We could encounter situations where we don't get a positive cell potential. Right? What's going to dictate how we flip our equations? Well, what's the reaction we're studying? So in this particular question, you've got to be very careful with how you approach it. This is not a voltaic cell. This is saying in this reaction, our citric acid cycle, okay, so I don't know why the computer's lagging a little bit. When we look at the citric acid or our Krebs cycle, one of the steps within that process is the conversion of it's a conversion of lots of different molecules, but one of the steps is the conversion of malate to oxaloacetate. Okay, that happens. Okay, so what we want to now go through and do is study that particular reaction. How do we convert malate to oxaloacetate? Through NAD+. This is a redox reaction. Because it's a redox reaction, we can look at cell potentials. The cell potentials, by definition, are always going to be given as the reduction potentials. And so you now need to manipulate those individual equations to match the equation we're studying. Does that make sense? So this does not necessarily mean we have a positive, or a negative for that matter, cell potential. You have to set it up to match the question being asked. Does that make sense? So with that, go ahead. Start getting it figured out. So where should we start this question? Any guesses?
What's being oxidized and reduced?
So what do you mean, what's being oxidized and what's being reduced?
Well, because the E cell is the E of the cathode minus the E of the anode.
Okay, so that formula isn't necessarily wrong, but it's one that I would never use because I don't memorize it well. But okay, go for it.
So it says malachite is oxidized by the anode.
Okay, so pause. Okay, so right there I think is the key point that you're making a statement of. Where we're starting isn't what's oxidized or what's reduced and then looking at cell potentials. We could care less about the cell potentials. What we care about is that this says malate is oxidized. Okay. The question says, I want the reaction where malate is oxidized. So I can now shift my focus. Again, cell potentials I don't care about. And I can look at the equation that I've got. Is malate being oxidized in the equation I'm given? No, malate's the product of that reaction. If I'm saying malate is oxidized and ultimately oxidized to, malate must be the reactant. So to be a reactant, what do I have to do to that equation? I'm going to have to flip it. So malate will go to the oxaloacetate plus our 2H plus our 2 electrons. Okay, we could go through and write our cell potential now as well. The cell potential as given was negative 0.166 volts, but what did we do? We flipped the equation, which means we should multiply by that negative, and that makes that positive. Okay, and I'm going to come back to your formula here in a second. Okay. How did that reaction happen? Well, that had to be combined with the next reaction. The next reaction, we don't want to flip. We'll get our 2 electrons plus our H plus our NAD plus. Why do I not want to flip it? the previous equation was oxidized. This one needs to be reduced if I'm going to run a complete redox reaction. The cell potential as given was negative 0.320 volts. I did not manipulate it. I did not flip the equation, so we'll leave it as is. And I could now go through and add up my two equations. My electrons would conveniently cancel. Some of the H plus cancels. And I would get my malate plus my NAD plus goes to the oxaloacetate, which I'm just going to leave as that, plus H plus NADH. All right, and then what's my cell potential? I just have to add up those values. 0.166 minus 0.320 gets me
Negative 0.154 volts.
volts. Okay? Does that make sense? Okay. Back to your statement about the formula, on what formula that you could go through and use. Okay, you'll have to remind me. You said E cell was equal to E
The cathode minus the anode.
of our reduction potential of the cathode, reduction of our anode. That formula is not wrong. It is perfectly acceptable and correct, right? But it requires that you have things tied. You would have to know what the anode is. You have to know what the cathode is. Okay? In certain systems, you have defined what those are, so it might be easier to use that formula. Right? This question didn't define the anode. It didn't define the cathode. So the only way you would determine what was anode and cathode is by walking through the process behind each of these. Okay, what do I mean by that? Well, the blue one lost electrons, because the electrons are a product. A loss of electrons is known as oxidation, and oxidation occurs at the anode, because we have anox. Okay? Once we've defined that, we would know the red one was a gain of electrons, which is reduction, which happens at the cathode. So you could then use your formula to process that. But the only reason that formula made sense is that you already knew which equation to flip. And if you already knew which equation to flip, you've already dealt with the sign change. You don't have to have this formula memorized. Right? So it's going to come down to which one you feel is easier to navigate. Okay? Based off of you sharing the formula with me, I would think you're more comfortable with the formula. That's perfectly acceptable. But you have to decide where your comfort is, and you need to stick to that. Right? Because in the method that we walked through, we just added the values up. We just had to recognize what we flipped. In the formula, right, you have to subtract one of your values. But you have to make sure you subtract the right one. And that is an extra layer of information that I personally suck at memorizing, and so I would avoid that at all costs. If you've got that nailed, go for it. Kind of make sense? Okay. Last part of the question is the reaction spontaneous? No, we have a negative cell potential. Okay? So I want to call out a little bit of attention on that. We got to make sure that we always answer all of the questions that are asked of us. Right? Because lots of people are missing simple questions like, solve for the delta G. And you solve for the delta G, and then you just move on. The next part of that question said, is this spontaneous or not? Right? So you're now missing needless points because you didn't provide that extra layer of interpretation. So make sure you read your questions carefully all the way through to actually answer the overall systems. Okay? So this would be a not spontaneous reaction. Okay? If it's not spontaneous, would this ever happen? It's a weird, vague question. Okay? If it's not spontaneous, it shouldn't happen on its own. Right? If it doesn't happen on its own, what happens to the Krebs cycle? What's the whole point of the Krebs cycle? To go around and round and round in continuing reactions. And we just said that one of the steps of this reaction doesn't happen. If that reaction doesn't happen, doesn't the Krebs cycle shut down? Yeah, that's literally what it means. Okay? Is that potentially a problem? Well, if the reaction never happens, yes, this is a problem. So something must be kind of missing within our system. Okay? Before we look at that missing thing, does it make sense for the reaction to not occur spontaneously? Okay? We can think through kind of simple examples. Brushing your teeth. Let's go with something that everybody can experience, right? Okay? Does brushing your teeth happen spontaneously? No, it doesn't. That requires some kind of energy input that we have to go through, get the toothpaste, brush. Okay? What if that was something that happened spontaneously? Anytime a brush hit your hand, what are you going to start doing? Brushing your teeth. Put a comb in your hand? Nope, not the hair, the teeth. Okay? Put a brush to brush your hair? Nope, not brush your teeth. Imagine fitting one of those things in your mouth. Okay? We don't want it to actually continue on its own. We want to control when that system happens. The exact same process is going to happen biologically. The biological system doesn't just want these reactions running constantly. It actually wants them to stop and only run when they want it to. Think about the production of energy. Do we just want energy produced all the time? No, because where's that energy going to go? Eventually, it's just going to go to heat. And what's going to happen to us if we just constantly produced energy? Take it to the extreme. Poof, fireball. Okay? So we don't want a constant production of energy. We want that to run only when we need it to run. Okay? Because maybe we need to save that energy because we're about to do something else. Okay? We want to control that production. So it absolutely makes sense that our reaction is non-spontaneous. But we have to make it spontaneous. How could we make it spontaneous? Right? If the voltage suddenly became positive, but how do I get the voltage become positive? It's negative right now. Right? We could think back to equilibria and just our chemical reactions. How do we change our reactions to become spontaneous? Okay? We could play with the concentrations of reagents. Okay? That can shift our balance to make it a spontaneous reaction. We could play with the temperature. That would cause things to shift. So that makes sense from Gibbs, but can we do that with cell potentials? We might be, well, we've never seen that. We've never seen a way to do that. Well, really, we've seen Gibbs free energy, our change, okay, was dependent on, what was it, RT ln of K? So if we change temperature, we could change our change in Gibbs free energy. If we changed K, okay, that equilibrium constant, we could change the spontaneity of the reaction. But we don't have anything to delta E. Or do we? Didn't we also say, I already forgot the equation. Crap. Delta G equals negative NFE. I think I did it. Right? So if delta G we know is tied to temperature in kelvins, or sorry, not kelvins, the K in this case is the equilibrium constant, and I know delta G is tied to the cell potential, what can I now tie to each other? Cell potential, temperature, and our equilibrium constant. All of those things can come together. And what does this come up with when someone went through and made this observation? That someone made a pretty cool observation, and we now know it as the Nernst equation. So if we switch up our system and now say, well, let's calculate the cell potential for the reaction at 37 degrees Celsius. We're changing the temperature. Where we were initially was at standard state. Standard state was what temperature? 25 degrees Celsius. We've increased the temperature. Right? That could have effects on our cell potential. So why 37 degrees Celsius? That's body temp. Why are we picking body temp? Where's the Krebs cycle happening? In our bodies. Okay? So we're mimicking that system. Okay? And pH 7. What is pH 7 in reference to? Say again?
Neutral.
Yes, it's neutral, but what is it referencing? How do you determine the pH?
Concentration of hydrogen and OH.
Okay? The pH has nothing to do with concentration of hydroxide. It has everything to do with concentration of hydronium, H3O+. Right? That's why it's pH. Right? A larger value meant there was less concentration of H+. You're right, when I have less concentration of H+, I have more of hydroxide, but that's technically the pOH scale. Okay? So we're now looking at pH 7, which is neutral. Why would we make it neutral? Why do we pick 37 degrees Celsius? Body. Why do we pick pH neutral? Our body's roughly neutral. Okay? And then when the ratio of the NAD plus to NADH is 700, what do those brackets mean? Concentration. And the concentrations of malate and oxaloacetate are equal. Okay? So we've been given a whole slew of extra information. Okay? And as soon as we see concentrations, we should immediately be thinking, what thing controls concentrations? Our equilibrium constant, okay? Our K. Okay? But in cell potentials, if we're at equilibrium, what's our cell potential? Okay? For our cell potential, what's happening? To get a cell potential, what has to happen? There must be a net flow of electrons. If we're at equilibrium, the forward reaction and the reverse reaction rates are the same, which means the electrons going forward equal the electrons going backwards. What's the net electric flow? 0. And if there's no electric flow, what's your cell potential? 0. Okay? So in this particular system, we want to be not at equilibrium. What's our not at equilibrium variable? Q. Right? Which is why when we look at the Nernst equation, what do we get for our Nernst equation? Our E cell, and note we won't use the little not, the little 0 in the upper right-hand corner, because this is no longer at standard conditions. Our E cell will equal our E cell at standard conditions, then what? Times the natural log of Q. So our equation gets significantly larger. And if you were wondering why I asked you what the equation was, I don't remember whether it's plus or minus. Sorry. Okay. So, with all of this information, can we possibly go through and see what the cell potential is? Cool. Prove it to me. Do it. So, a couple things. What I started to do was just drop in numbers. So that red value, our 0.154 volts, that came from solving our standard cell potential off the previous slide. Okay, so that's why we set that up, so we can see that. That then moves in. There was this question of, well, but it's 0, because we're at equilibrium. We aren't at equilibrium. That's why it says Q, not K. If I'm at equilibrium, this Q becomes K, and what happens? That will equal the negative of my standard cell potential. Or the opposite. It'll actually, sorry, because there's negative there. It will equal my standard cell potential, which means the cell potential minus that will equal 0. But that's when I'm at equilibrium. Do we know what the equilibrium constant is? Yeah? Give me the number for what the equilibrium constant is. Okay? So let's walk through what the equilibrium constant would be on how we would go through and solve it. Okay? Same process for Q, so it's going to be relevant. We'll go ahead and write it in after our natural log. How do we solve for our equilibrium constant? What do we need? The products. What are my products? Oxaloacetate. No one's got time to write that out. So the concentration of oxaloacetate. Okay? Now what? Times my NADH.
Times H plus.
Times H plus. Right, and then what do? Divide it by concentration of my reactants. What are my reactions? Malate, NAD plus, and that was it. Okay? And we might go through and say, well, I can sub those numbers in, and if you're on that fence, you can go through, you could say that. Yes. Does that mean you're at equilibrium? No, there's zero context to say that you're at equilibrium with those numbers. Okay? The only way we would know what the equilibrium constant was is if we were told the numbers, okay, for what the equilibrium constant was, or we were told the equilibrium concentrations. Were we told we were at equilibrium? No. So we have zero information about what the equilibrium constant is for this overall reaction. There's nothing that you can touch to drop in any information saying you are at equilibrium. And because of that, this zero that we're dropping in real early on is utterly nonsense. It's only zero when we are at equilibrium. We don't know. Until we know that, you can't go through and just say you're at zero. Right? Which sets us up with the next question. Right? To solve for ln of Q, I still need all of the numbers. I need all of those concentrations. Am I given them? But I don't see a single number for my oxaloacetate. But I'm told the concentration of malate and oxaloacetate are equal. So let's pick a number for oxaloacetate. Let's pick 10 to the negative 3.64. Whoa, that's an ugly number. We don't want to deal with that. What's my concentration of malate?
Same thing, so they cancel out.
Doesn't matter what I put, they cancel out. I don't have to worry about it. Okay? Am I given the concentration of NADH?
Not directly.
No, what am I given?
You're given the ratio of NAD plus over NADH.
I'm told NAD plus over NADH equals 700. What do I want? I want the inverse. So instead of saying this, what numbers can I put in? 1 over 700. So when you, it's just 700. No, it's not. It's 1 over 700. And now we're stuck. How do I get the concentration of H plus? We're told the pH. And because we remember our last unit, we know pH is equal to the negative log of the concentration of H3O plus, also known as H plus. I know that the H plus concentration is 10 to the negative 7. Do I have all my numbers? Yep, which means I can now go through and solve. What do I get for a number?
I got 0.149.
Okay? And I would argue again, just for sake of numbers, okay, it's not that we got 0.149 volts or even 0.149 volts. It's that we got positive, and underlying it makes it look like plus minus, but we got a positive 0.149 volts. Can anybody second? Can anybody second the number? 0.15? Yeah, so it looks like there's just a rounding thing in there from either one of you. Who cares? Ultimately, we're in the right ballpark. We're okay with that. So what happened to our cell potential? We went from negative to now positive. So a couple things can come out of this. Number one, are we at equilibrium with these concentrations? No. Why? Because the cell potential at these conditions is not zero. So we're not at equilibrium. Right? So we know that. We also know, since it's now positive, that this reaction is now spontaneous, and the reaction is going to continue. Okay? So in a biological system, what's happening? We can control whether this reaction moves forward by changing temperature, the concentrations of NAD plus and NADH, and our pH. Okay? Could we change the concentrations of malate and oxaloacetate? Probably, but in a biological system, those two concentrations are probably pretty close to the same. Okay? Just because of how they're getting used and produced within the chemical reaction. So their concentrations are probably pretty close to the same regardless. But the NAD plus and the NADH are an active oxidizing and reducing agent, depending on which way you're looking at it, and those are going to get pumped in when we need to run the reaction. Right? We could look at changing the pH. We could look at changing temperatures. Our biological systems can now control whether this reaction moves forward or not. That's pretty wicked. Go ahead.
I'm not really sure. No, I understand that you got the 2 moles for your electrons transferred from the original problem. I'm just not really sure why we say, oh, it's 2 moles of electrons instead of like maybe, oh, it's -2. Because I understand that we cancel them out, and at equilibrium, that would be 0. I'm just not sure why it would specifically be 2. Is it because when you have the 2 reactions here, you have 2, in the original problem, you have 2 electrons both on the reactant side, and then we can say, I'm not really sure how that is.
So when we're talking about the electrons transferred, it's not which one was gained or lost, it's just how many electrons were transferred. So for one thing, what did it do? It gave up 2 electrons. What did the other thing do? It accepted 2 electrons. How many electrons were necessary to cause those reactions to happen?
2.
2. So it's the absolute value of your gain loss.
Okay.
So it will always be a positive for your electrons transferred.
So if you know NAD plus and NADH
Are they equal?
or the ratio, we know the ratio.
We know the ratio in this case, yes.
So like we're supposed to assume everything else like malate and oxalate.
Should we just blanket assume that the malate and oxaloacetate are always equal to 1? Or always equal to each other?
Why we why we assume?
No, we didn't assume it at all.
How do we know that?
Reread the question.
Oh.
The question tells us they're equal to each other. That's not an assumption made on our part. That was a statement of fact from the question. So you have to use that given information appropriately.
And then we're usually supposed to know then.
And then are you responsible for knowing how to determine H plus from pH? Yeah. Right? Why are you responsible for knowing that? That was our last unit. Okay? So believe it or not, you're starting to move into content areas where your knowledge only builds on prior knowledge. So you can't forget past knowledge. For those of you that have to move into more chemistry, it becomes even worse. Right? In organic chemistry, we will quote stuff from 151. We'll quote stuff from 152. And if you have weaknesses in those spots, those get exploited in organic chemistry. Not intentionally, okay? But we're trying to build content on that knowledge. And if you don't have that knowledge, what do you have to do to try and get your way through organic chemistry? Memorize. Okay? And so if your entire process so far, I'm just going to memorize enough for this test, enough for this test, enough for this test, that gets you through Gen Chem fairly well. For OChem, what you'll see is the exam averages do a funny thing. Exam 1, usually fine. Exam 2, it drops by about 5 to 10%. Exam 3, it drops by another 5 to 10%. Okay? My class, there's only 3 exams. Some classes have 4 exams. Guess what happens on the 4th exam? Drops by another 5 to 10%. And you go, oh, but we can reset in OChem 2. No, you don't. Start from your final exam in OChem 1, look at its average. Look at the average for exam 1 in OChem 2, drops by another 5 to 10% from the bottom of OChem 1. That's nasty because all of the content ties. So if you have any weakness early on, it continues to destroy you throughout the rest of the semester or the rest of your year. Okay? So if you got to take OChem, pay attention early on because it's only going to get worse as it continues. Right? And if you can flip it and spend more time building up, what you'll see is actually student learning go up the other direction. Okay? So you can take students that are weak at the beginning but recognize the weakness and slowly improve. And by the time exam 2 rolls around and OChem 2, it's easy for them. Okay? So don't just memorize your way through things. It will hurt you. Okay? Different lesson for a different day. So for today, if we take a look at this same system, we're talking about biological systems. And in cells, the concentrations of our individual substances are highly regulated. So if we look at the cytosol or in our nucleus, the concentration of NAD plus to NADH is 8 to 1. Or 8, sorry, that's not an 8. An 800 to 1. If you move into the mitochondria, it's now 7 to 1. Whoa, that's wicked. Why? What's the role of the mitochondria? Oh, come on. Wednesday did better than that. What's the role of the mitochondria? Powerhouse of the cell. Thank you. Okay? So that is going to change the ratio between those species because its role is different than what the nucleus is. The nucleus isn't trying to produce power. It's trying to maintain genetic information so that the cell can continue to replicate and live onwards. Okay? So generally speaking, you don't want a lot of power in your nucleus because you put a lot of power into the nucleus, what's going to happen to your genetic information? It's going to get destroyed. Okay? So, what we're now about to set up is a little bit kind of a shift. We're going to start whipping through some slides because these slides, I would argue, are more just informational. Okay? Some of them are practice based off of our electrochemical cell stuff. So they're just kind of repetition. I would argue what we need to do is get beyond the practice into the content that we need for next week, which would be our semiconductor content. So what we're going to do is slide through a whole bunch of these, and then next week we can double back and look at practice. Make sense? Okay. So if you get dizzy, stop watching. A little bit of review, we'll look at metal elements. So when we look at metal elements and we put them together, what we end up coming up with is this model known as an electron sea. Okay? And what's largely happening here, particularly if you've read the background information, is that when we look at how metals bond to each other in a larger system, they have very weak connections. Okay? They have very low electronegativities. They don't hold on to their electrons. And so they aren't trying to grab more electrons from other atoms. So they essentially just kind of, it's not float, they're packed into a solid, okay? But they aren't strongly trying to grab electrons from other atoms. And if you try to grab electrons from other atoms, what happens to the distance between those atoms? If I try to steal money from any one of you, what's going to happen to the distance between me and that person? It's going to get real, real close. But I can only steal money from maybe 1, 2, or 3 of you. The rest of you would then be safe. Okay? Only the people within my reach would be able to have money stolen from them, and they don't even know. Okay? Everybody else is like, this is hilarious. Okay? The same kind of thing is happening with our metals. Okay? Where we're looking at that currency as our electrons. Okay? They don't really need to hold on to their electrons. They're not trying to steal electrons from other things, which means the electrons just kind of float into this big mass of just electrons floating through our system. Okay? Why does this become important? Well, what about conductivity? Should electrons or should metals conduct electricity well? Yeah? Why? What is electricity? The flow of electrons. And if our metals aren't holding on to those electrons, we should be able to pass electrons through them very, very easily. Okay? And sure enough, what's one of our primary qualities of our metals? They conduct electricity. Okay? If we go through and look at kind of bonding of metals, this gets a little bit hairy, so kind of deal with me a little bit. If we looked at, say, sodium, we can look at its orbital diagram. Okay, sodium wants to be +1, so this outermost electron of our 3s kind of floats off and is now contributing to that sea of electrons. If we look at the rest of the electrons, they're all partnered and paired up, so they're relatively stable, and there isn't a nice place to kind of put extra electrons in or pull electrons out of. Okay? That 3s is really the only one. Okay? What does this mean for us? When we now take a whole bunch of sodium atoms and we bring them all together, what we're going to encounter is kind of two sections. We'll have a section where we look at all the valence electrons that are now all aligning across the entire C, and then we'll look at this other section that's empty orbitals. Okay? And what we'll notice is the gap in energy between our empty orbitals and our filled orbitals is almost non-existent. Okay, why does this become a big deal? I can push electrons in, say push electric current into this system. This very quickly promotes an electron up here, and once we're in that empty orbital, what can that electron do? Well, it can jump from empty orbital to empty orbital to empty orbital, and we can pass that electron all the way across. So we can get from one side of the metal to the other side of the metal very efficiently. Kind of makes sense? Okay. So metals are good conductors of electricity. We'll use extra words. We'll talk about delocalized electrons. Okay, delocalized electrons means the electrons aren't in a particular location. When we think about an atom, we'd say our electrons are on an atom. When we look at metals, all those atoms are aligned there, and they don't care about their electrons, and so the electrons can move from atom to atom to atom really, really efficiently. Okay? So that's referencing that the electrons are delocalized. That term shows up again in organic chemistry if you need it. Okay? This is why our metals are used for wiring in electrical devices. Why does it do this? This is so weird. Okay, come on, go forward. Now you're going forward too much. Well, we have metals. We also have not metals, right? Okay, so what's the difference? So our not metals are covalent molecules, and they tend to be poor conductors of electricity. Okay, well, why? So a couple things come into play. Number one, they have relatively high electronegativity. So if I compare any of my non-metals to my metals, what you'll notice is that all the non-metals are on the side of the periodic table where we have the highest electronegativity. Okay? So fluorine's the most, cesium's are least. Our high electronegative elements are all pooled in the non-metal category. Okay? What does that mean? They're electronegative. They really want to hold their electrons. Okay? And not only do they want to hold their electrons, they want to steal electrons from other atoms. Okay? So now that stealing thing comes into play. In the metal, they didn't care. They can be near anybody, and not a big deal, because we're not going to try and steal anybody's currency. Our non-metals are now like, nope, I need to steal currency. I need to get more electrons. And because of that need, that now draws the atoms tighter and closer to each other. That tighter and closer creates a stronger attraction between individual atoms and the individual electrons within the bulk material. What does that ultimately mean? I don't get a sea of electrons. Right? How does this change our system? Well, number one, we don't conduct electricity. Well, why not? Okay, again, looking to our bonding pattern can come into play to help us. So if we look at our orbital diagram for carbon, right, we've got that system, and we now put it together into a bulk material. A bulk material is what we're seeing on the right. We're still going to get the same system. Okay? The valence band is all the orbitals that have electrons in them. And what starts to happen is that we note a gap appears between the conductive band and the valence band. Okay? That gap is due to a variety of different features that we're still technically working out a little bit. Okay? And we're still actively studying. One thing that you could consider when we look at this is that when we consider our bonding in metals, we're looking at trying to move electrons from occupied orbitals to unoccupied orbitals. The jump there is actually relatively large. If we go for carbon from 2p to 3s, that's a relatively big jump, okay, in energy. So to do that promotion requires lots and lots of energy. Okay? So much energy that if we tried to put electricity in to cause it to happen, it doesn't do it very well. And because the electricity energy that I have to put in is so high, what do we end up saying? Okay, if I got to pump electrons from my load, from my battery into this, I got to push real hard. I have to push so hard that I get an electron to jump up to there. It requires so much energy to force that jump that do we see the electron move through our sample? No. To get it to make that jump requires enough energy to clear that band gap. Whereas in the metal, that band gap was non-existent. Immediately up and in, no problems. Here, there's some barrier to that jump. That's our insulating properties for our nonmetals. Okay? So if we look at them together, we can get a better feel for this. Our metals have this non-existent barrier. So as soon as I put a little bit of energy or a little extra electrons in, I immediately get a jump and my electron can free flow throughout that entire material. If we look at the nonmetals, I have to put a whole lot more energy in to force the electron to make that jump. Okay? So much so that we would reference that material as being non-conducting of electricity. Kind of makes sense? Okay. Well, what else do we have? Well, we just have metals and nonmetals? No, what else do we have? Is iron a metal? Yeah, it's considered a metal, and it's also considered part of the transition metals. Transition metals are still metals. What do we have other than metals and nonmetals? Semi-metals or our metalloids. Okay? This is now talking about our semiconductors. Okay, so on that diagonal, we're transitioning in properties between our metals and our nonmetals. Okay? Because our nonmetals being on the metals being on the extreme left, zero band gap. On our extreme right, we have a large band gap. As we move across the table, what must eventually happen to that band gap? It has to start changing somehow. And where that change occurs, or is most noted, is when we're looking at our semiconductors or our semi-metals. So we could go through and look at silicon. Silicon's an interesting one to look at. Okay? Why is silicon an interesting element to look at, particularly in light of what we looked at for our nonmetal? What was the nonmetal element we looked at? Carbon. And now we're going to look at silicon. Why are those two an interesting partner to pick? How many valence electrons does carbon have? 4. How many valence electrons does silicon have? 4. They're in the same family. In fact, they're in the same family. We might predict similar chemical properties. And yet, we don't. Silicon starts to change its properties a little bit. The band gap in silicon gets small enough that we can force electrons through, given enough energy. That enough energy is small enough that we can actually modulate that. Okay? What do we mean by that? Well, we could put in enough energy and no electron jumps. That would correspond to what? No electron motion, and we might call that a 0. Or we give it enough energy and our electron jumps. Now we have conductivity. That might equate to a 1. And what have I just created? A bunch of you are supposed to be engineers. We now have binary code. Okay? So depending on our electric flow, we could actually use semiconductors to create 1s and 0s for coding information as far as computer code goes. That's pretty neat. And all we have to do is modulate the electric current to navigate this. Okay? Could we use carbon? Sure. But the power load that we have to put in to force our 1s and 0s is now so astronomically high, it doesn't make any sense to use as a material. Okay? So neat. Silicon happens to match this. But carbon has the exact same electron configuration. Why is silicon different than carbon? I'd argue there's two big things that make it different. How is carbon different than silicon?
Size.
Technically, I gave you a hint. Okay, two big things that make them different. Silicon is larger. Why does that matter? When we looked at carbon's electron configuration, same. For carbon, we were talking about how do I move an electron from the 2p to the empty 3s. For silicon, what am I talking about? How do I move an electron from the 3p to the empty 4s? That gap in energy versus this gap in energy is different. You're still talking about the same jump, p to s. Why is it different? Remember how I said content continues? Do you remember in 151 you talked about atomic theory and where all of our energy of our orbitals was? And that as we go up in energy, what happens to the distance between our energy levels? They get smaller and smaller and smaller. So silicon being larger, that gap between exciting my electron from that low energy state to a high energy state is smaller than it is for carbon. That could correlate to our band gap. Okay? What else is the difference between carbon and silicon? Say again? Mass isn't ultimately going to matter too much because what are we concerned about moving through this? Electrons. So what else could we look at that has anything to do with electrons? If not size, we also have electronegativity. Carbon being more electronegative than silicon is pulling those electrons a little bit tighter and holding. Why is it? Well, we've got that difference in energy levels between those gaps. Okay? The electronegativity is partially explained by that also. Okay? So we can leverage both of those things to help explain why silicon suddenly switches. Okay? Do we know fully why? I don't think we know fully why yet, but what we're looking at is how that works. And once we have some understanding of how it works, what can we start to do? We can bring in other materials that mimic silicon. And in the process of changing the materials, what's going to happen to the band gap? It's going to fluctuate. It could get smaller. It could get larger. And depending on what I want to use that semiconductor for, that material may be a better or more optimal choice for that band gap. Right? So what we would shift to within the semiconductor field is now, how do I mix in other elements and what band gap is produced out of that? Once I know what that band gap is, now what material or where would that be useful for? That's kind of a neat process. Okay? Which then sets us up a little bit with how LEDs and solar panels work. We'll talk about it a little bit more of kind of a half-assed system first. If we look at LEDs, what happens with LEDs? You've heard of an LED, right? They light up, okay? So the whole point of an LED is to light up. So I just hold on to an LED and go, boop, there it's glowing. No, what happens? It needs energy, okay? So what we would do is pump electrons into our semiconductor. When we pump electrons into the semiconductor, the valence band was all full. So what happens? It ejects an electron up into the conduction band. Okay? That electron could move around a little bit, but it's at a high energy state. Eventually, what does it want to do? Come back down. As it comes back down, we could look at that electron coming back down and then continuing our loop around through our battery system. Cool. But if it's dropping in energy, can we destroy that energy? No. Where did that energy go? The energy to go up came from us putting a battery into it, giving it energy. What happens to the energy when it comes down? The electron goes back down, but the electron's a different energy now. What happened to the energy from where it was high to now where it's low, where it can continue around? That loss in energy comes out as light. Typically, we'd represent as h nu, okay, or h times our frequency. Okay, that is our light. Okay, so when we're looking at LEDs, what's happening? We've put a bunch of electricity in. That caused an electron to jump. The electron came back down, and ta-da, I get light. What color light would I get? These are blue lights? What's going to dictate the color of light I get? Say again? The energy of the band gap. If that's a large energy band gap, what color light am I going to get? 151 again. That was interesting. Yeah, the light just came on. Did you just go red?
Red.
You were just trying to hide that you were saying red? Okay. That is something that we should theoretically remember when we first talked about visible light and all of those things. We typically forget it. That's okay. Okay. For me, to help out with it, okay, when I step outside in Arizona, what am I concerned about? Heat?
UV.
What was that?
UV.
UV. I care about ultraviolet light, because what's the ultraviolet light going to do to me? It's not that it's burning you up. That ultraviolet light hits your skin and causes cell damage. It's a high energy which breaks apart your cells. Okay? Why is it? Well, then what does it do once it breaks apart our cells? It can cause damage to our DNA, and when our DNA gets damaged, it increases the risk of mutations, and those mutations could lead to cancer. So we want to protect ourselves from the UV light because it's so high energy. I don't care about the heat necessarily, okay? But what I care about is that UV kind of first and foremost, because that's going to kill the skin. Okay? So UV was high energy. What color visible light is closest to UV? Red or violet? Violet is our high energy. Red is on the opposite end of the spectrum from our violet, and red is actually the lowest energy. So the larger my band gap, the more the more violet my emission. Okay? But if we look up here, do I see blue? No, I see white. Why do I see white? We step outside, what color light do we see? We also see white. Is the light outside white? What makes it? All the colors, which is why when it rains, we see rainbows showing the full spectrum of colors. So if we're hit with all of the wavelengths, we interpret that as white light. If our LEDs were only blue energy, what are we going to see as our light? We're going to see blue, because that's all that's coming out of it. How can I see it as white? I need multiple LEDs. So if you actually look real carefully at some LEDs, depending on their design, you'll see that they are both blue, green, and red. Because when you have all three of those lights together, that now tricks our eyes into seeing white light. And you can vary the intensity of those individual LEDs to change from warm light to cool light or whatever the hell the other colors are. Okay? There's another process that you can do it that was leveraged when we talk about fluorescent lights. Fluorescent lights, you put a cattle prod of enough energy in, creates a big excitation. That excitation relaxes, and what it ends up hitting is something known as a phosphor. The phosphor is then what emits the light. Okay? Same deal, you need a bunch of different phosphors to emit different energy lights or different energy wavelengths so that we could see more of a white light come out of it. So depending on the design, you see a variety of different fashions. Okay, so cool, that's how LEDs more or less work. What do solar cells do? What's the point of solar cells? So LEDs We add energy. What's the point of a solar cell?
Take it.
Okay? We want to produce energy. How does it work? What does the solar radiation do? Light comes in, exciting an electron. That electron now has the ability to start moving because it's now moved into the conduction band. As that electron moves, we leverage the motion of the electron to replace it to create our current. It's using the same material? Yeah, more or less. Probably a little bit more on the less, but same idea. Okay? But you're changing, you're kind of flipping how that system is working. LEDs, we put energy in to force light out. In solar cells, we use light in to force energy out. Okay? Where are we? More or less okay. So, we've got our review. Our semi-metals have a smaller band gap than our non-metals, and our metals have the smallest band gap possible, which sets us up for, we're just going to skip that, for this question. Rank the following elements from smallest to largest energy band gap. Like, how can I possibly figure out the energies of those band gaps? Because we haven't quantified any of those. You're right, we haven't. What did we do? We said metal was the smallest and our non-metals were the largest. So really, what could we go through and do to answer this question? Separate our metals from our non-metals. Where's Fe? Iron, in our transition metals, is a metal. That's going to have a very small band gap. Okay? If I looked at an element further to the left of iron, we might predict it to have a smaller band gap. Okay? But since iron's a metal, we're looking at a non-existent band gap as far as we're concerned. We could then go through and look at phosphorus. Where's phosphorus? It's a non-metal, which means this is going to be our largest. Gallium sits in a weird space. Gallium is pretty much right on top of that staircase. And what was that staircase? Our metalloids were really darn close to being a metalloid. I may have spelled that wrong, but close enough. Which means this is our intermediate band gap. All we're really being asked to do is to classify metal or non-metal, and then where we are relative to those systems. The more metallic we are, the smaller the band gap. The less metallic we are, the larger the band gap. Okay? Keep it as simple as possible within that. Okay? This slide still gives me nerves because of the question, and I still not 100% on it, but we're close enough. Okay, so silicon is used in semiconductors, ultimately because probably first and foremost, abundance is going to be the largest aspect behind it, but it's also the first element on our table, which is partly tied to abundance, that hits this kind of perfect spot where the band gap in that pure material just happens to be at the proper energy, so that when we put energy in, we don't have to put that much in to cause conductivity. All right? So if we go through and look at it, 4 valence electrons and half-filled valence orbitals tend to be part of that contribution. Remember, carbon had that same system, but carbon wasn't able to conduct because of where it's located. Higher up on the table means the gap between our energy levels is significantly larger. Okay? So if we now move to composite materials. So as we find that silicon works, we want to find other materials that could potentially do the same thing. So which of these composite materials could also act as semiconductors? Okay, well, the big thing that we're trying to tip in on here is trying to get to that 4 valence electrons, okay, as kind of our bulk system. So within that, if we looked at gallium and arsenic. So gallium, 1, 2. Gallium, where'd it go? Third row, so we're 1, 2, 3, right? Yes, good. At least one person's with me. What's arsenic look like? Okay. Arsenic, with where it's located, is in that fifth row, which means we have 5 valence electrons. 1, 2, 3, 4, 5. What do you see? We got our 4 valence. Why is that 4 valence magic? It's what silicon has. Okay? That matches that system. Where was gallium? Which row? Sorry, not row, the other option. Column. Which column was gallium in?
Third.
Third. Which column was arsenic in?
Third.
It's not in the third, it's in the fifth. And what we get is a 3-5 semiconductor. So if we talk about conductors or semiconductors, you'll hear 3-5. Right? Why 3-5? Because again, when we look at those valence systems, you're going to end up with a system that hits you those 4 valence electrons. Right? And for people being like, but aren't those different energy levels? We're not concerned about that in the bulk material. Those electrons will align in that system. So cadmium and sulfur is going to be a little bit trickier to deal with. Okay? And we'll come back to that one in a second. How about indium and phosphorus? Where's indium? 3. Where's phosphorus? What do we have? We have a 3-5 material, which means that could work as a semiconductor. Where's gallium? Where's selenium? 6. Is that going to work? If we look at 3-6, that's going to add an extra electron. If we look at that valence system, do we have it all with 4 electrons? We've bumped up to that 5. That changes the balance for our gallium selenide, which then means we're less of a quality semiconductor. What happens when we look at the cadmium and the sulfur? How many valence electrons does cadmium have? Cadmium is tricky because it's in the transition metals, but the name above helps us out. Cadmium has a Roman numeral of 2. It has 2 valence electrons. Where's sulfur? 6. If we were to propagate this one out, there's our cadmium in red. What's going on with our sulfur? With 6, I've got 2, actually I did that right? 2, 4, yep, 6. You mean, well, this doesn't work, except what can we potentially do? Interestingly enough, we can take that paired electron and we can promote it over to the other side. And now what do we magically have? We've got 4, which means that also works. So when we're looking for our semiconductors, 3 5s work as composites and 2 6s also work as composite semiconductors. Those are the 2 most common ones that we would address for being good semiconductors. Go ahead. It is D10, but if we're considering valence, what are we looking at? S and Ps. Yep, we skip over the d orbitals when we talk about valence electrons. Okay, I know we're right there, but I do want to get to at least this statement. Yeah, I don't want to look at that one quite yet. Come on, stop it. Okay, for doping in semiconductors. So in doping, we can go through and we can take a standard semiconductor and it's got a normal band gap. And what we can now do is we can dope it. By doping, we add something else, just like you would do with athletes, right? They have their natural strength and we dope them so that they get stronger, faster, better. Okay? In semiconductors, we have 2 ways that we can dope. We can do what's known as N-type doping, N standing for negative. What things are negative? Electrons. So if we're N-type doping, we're putting an element in there that has more electrons than our silicon. What elements have more electrons than silicon? And we got to be careful with that, more valence electrons than silicon. Phosphorus does, sulfur does, fluorine does. That's not in the same row. We actually don't care. All we care about is the number of valence electrons. So to N-type dope, anything to the right of silicon has more electrons and therefore would satisfy N-type doping. If we look at P-type, the P is standing for positive. So in a P-type doping system, I need fewer electrons so that I'm more positive overall. So what elements have fewer valence electrons than silicon?
Aluminum, magnesium.
Anything to the left of silicon. We don't care about the rows in this case. We just care to the left and to the right. That satisfies our P versus our N-type doping. Okay? With that, I will go